Yes. Okay. in the video.
This happens.
That's
not the right one.
You
Okay,
have
and then if you go, no, just do this one.
Oh, you
it
do
doesn't-
this.
Yeah, you can do this, and then you can do right both ways.
There you go.
Well, actually, I think you should do. Sorry, you should do the window and not the desktop, because then if there's audio in the videos, it won't share it. So you do, yeah, this one.
and the video is
Yeah, it's blurred. It'll be blurred, but it'll just show you. It doesn't even show this.
I think it's just because of the
Oh, it's the
it's just a
blurred
zooming,
background.
it's a zoom setting.
Here's the thing. But this isn't live. That's the problem. I don't know what just happened.
I think it's just because you've clicked out of the window.
Yeah, but I can't click on that window is what I'm saying.
But if you,
That's
Do we need that? Just share the,
yeah, that's why
I guess just
that's
share
why you
the-
just share the desktop.
okay, yeah, that's
is your background blurring active?
Mm-hmm.
yeah. Just turn that on.
Yeah. Okay.
It's you go. Oh. It's in, I think, video settings.
Nope.
Video.
Background.
Blur my
Yeah,
background.
that one.
There you go.
Okay.
There you go.
Hopefully it doesn't I've never seen that.
They give you cups, so Steven, for coffee.
They didn't give cups?
Oh,
there's cups here.
Oh,
Oh, okay.
relax. It's fast.
Just like the practice.
I think unless people here. Yeah.
Yeah, there is less people. They didn't get creamer. No creamer at
Three in there.
Oh, okay, yes, it's in the it's in that cup.
Get everything.
This is decent.
This one makes no sense.
Oh, hey, John.
Hey, Steven.
This, I know you have texture stuff, but there's some cookies over there that are home baked.
I'll send the other side to balance the room.
Okay. Thanks. They're standard issue.
Rob says hi and good luck.
Oh, okay. Thanks. Thanks, Rob. It's also coffee. Yeah. I also didn't drink coffee.
Yeah. No coffee.
We're currently waiting on my co-advisor.
No.
Not yet. I guess I have to have this closed.
Like a stirring. Yep, yeah. It's very clean, very sanitary. Changing their all design, crazy. They're very productive. They're productive.
Three. Hopefully she didn't mix up the time. She is oh no, she's the same time zone. Yeah, never mind. are the cookies? Are they okay?
They're good. I'll eat the lemon ones.
Okay, good. I baked less eggs because people typically don't like that flavor. But-
I'm trying to get this one.
You bake them?
Well, my girlfriend baked them while I stood next to her and did my habits. Yeah,
I see, I understand.
yes.
So let me unmute and.
Hello, hello,
yeah.
Steven.
Thanks for being here.
Yeah, of course. Are you ready?
I guess like ready as I'll ever be.
Yes, you're so ready.
Yeah.
Hey,
Hi, hi, how are you?
how are you? Good. Can you mute? So I
Hello.
finish my, yeah.
Oh,
Hi,
yep,
GH.
I'm muted
All right.
now.
So we should start because people are leaving. Hello, everyone. Thank you for joining this event. Today is Stephen Misenti's master thesis defense. The title is on the board, so I'm not going to repeat it. So the structure. Today we're going to have around 40 minutes, hopefully,
Hopefully.
of presentation, and then we have question from the audience. There are 3 people here. I see 1 person on Zoom, other than the committee members. And then people have to leave the room. Committee member asks question from Stephen, and then we kick him out. Discussion between committee members, and we call him back. So I don't want to waste any time. Thank you for both of you, Kishir and Yuan, for agreeing to be on his committee.
Thank you.
He's done a lot of work in comparing robots, and he did a lot of experiment. He had 120 slides. I told him he needs to compress everything, so has a lot to talk about.
Yes, and those 120 wasn't everything either. It's
All right, so I leave it to
Okay,
wanna
thank you.
unmute.
I'm gonna unmute now. All right. Yes, thank you for being here today. I'm gonna talk about my evaluation of 2 quadruped robots on dynamic rigid surfaces. Oh. All right, this is one we talk about today. Mainly going to go over the design setup for my tests and the analyses of the data that I recorded. There's a need for evaluation of current commercial quadrupeds to determine their stability performance within non-inertial frames. Legged robots have inherent functions that wheeled and tracked robots don't, such as being able to cross non-uniform terrain, having omnidirectional travel, and the ability to traverse stairs and other raised platforms. All right. There's a need for legged controllers for there's a need for controllers for legged robots that enable locomotion in non-inertial frames, such as trains, boats, airplanes, and offshore platforms. And there's also a need for an evaluation of these controllers and robot systems from an outside perspective. And here's some videos of Spot during my field experiments that show that the robot struggled to move about. Some of the most important qualities of legged robots include stability. Without stability, the legged robots will fall over. Recently, researchers have been trying to improve legged locomotion in natural terrain and on uneven surfaces. Dynamic rigid surfaces, non-inertial frames have an adverse effect on locomotion and manipulation within them due to disturbances. And there isn't all that much research currently being conducted of robots on dynamic rigid surfaces, but some works include vertically moving surfaces and deforming surfaces. These are my contributions for today that I'm showcasing, which is developing a testing and safety procedure for legged robots on dynamic rigid surfaces, designing and constructing safety harnesses and other apparatus for said robots, identifying shipboard motions from live IMU data from my field experiments, and the evaluation of 2 commercial quadrupeds to determine performance gaps. Here is my method and design. First robot that I tested on was Boston Dynamics Spot. One thing to note is that the torque limits that was reported by Boston Dynamics does not match what data I recorded. The data that I record exceeds these limits. This is Ghost Robotics Vision 60. This is the second robot that I'm testing. One thing to note is that the Vision 60 weighs more than Spot, but has a smaller payload capacity. This is a little size comparison between Spot and Vision 60. You can see that Vision 60 is a bit bigger, and the arm is a bit bigger as well. This is the arm that is on Vision 60 because Vision 60 does not have its own arm. Most important features of it is the 7 degrees of freedom and its reach, which is just a tad longer than Spot's arm's reach. In order to mount the Kinova arm onto the Vision 60's rails, I need to design and machine a base plate for it. The original base plate did not fit on Vision 60's rails, and so that's why I had to machine it. It's also machined using just one part in order to reduce the points of failure. Part of my contribution is also creating the safety harnesses, as I mentioned. There's a safety harness for Vision 60 and one for Spot. They were designed in mind to prevent impact during my control experiments and protect the safety of the robot. My control experiments were conducted on a Motec M-Gate treadmill. This was used to create or simulate a naval boat rocking in waves. It can pitch forward and backwards 10 degrees and sway left and right 5 centimeters. One thing that is lacking is the vertical motion that is most notable in during sea. That is most notable on ships at sea. For my experiments, I also needed to construct an attachment for the treadmill that I mentioned earlier. This was used to attach a fiducial for some of the tracking. And the platform that you can see was used to protect the treadmill from the robot's impacts. 14 motion capture markers were used, 9 on Spot and 5 on the treadmill. There were 9 used on both robots. 4 were put on the trunk, 1 on each foot and 1 on the end effector. And for the treadmill markers, there was 1 on each corner of the platform and 1 by the fiducial. The field experiments were conducted at Norfolk Naval Base aboard the M80 Stiletto. This was facilitated with the help from NRL, Naval Research Labs. These are the field experiments that I conducted aboard the Stiletto. Each trial was 3 to 6 minutes, and there was unfortunately only 1 trial per experiment type. 4 wave states were conducted on, which is the at pier, underway, C state, and S curves. At pier was at 0 knots, underway was 10 knots, and the C state and S curves were at 20 knots. The underway and C state the boat was going through rectangular motions, whereas the S curves were doing serpentine patterns. These are the control experiments that were performed on Vision 60 and Spot. The baseline has no treadmill motion. The just arm experiments only utilize the arm, the legs weren't moving. The just body only used the legs, the arm wasn't moving. And the both is when both the legs and the arm was moving during the experiments. These are motions 1 and 2. motion one has the pitch going about half the performance of what the treadmill is capable of, whereas motion two is almost a full performance. It also has a faster frequency for both the pitch and the sway. For motion three, I used the field experiments or IMU data collected from the field experiments to get in a motion equation for the pitch and the sway. I took the data, parsed it, and performed a fast Fourier transform on it to get the wave amplitudes and frequencies, and then found the peaks of the amplitudes. I then double integrated using trapezoidal integration method and found differences between the bow and stern IMUs to get the pitch equations. And then I performed I got the Euclidean of the X and Y to get the sway equations. Those were then normalized and translated so that they fit within the realm of what the treadmill is capable of. This is what they look like when plotted. And this is what motion three looks like. This is at ×5 speed. We can see that the treadmill has some sudden pitching movements and swaying movements. These are the metrics that I perform my analyses on. Joint data, the efforts and angles, support polygons, or measuring where the center of mass is within the support polygon, and the motion capture was used for the trajectory data, trying to figure out how much the robots deviated and what their trunk orientation was. Part of my contributions is producing the testing and safety procedures. There are 3 phases for this. There's the before the testing day, where you design the safety setup, do some preliminary testing on the robots, figuring out what it's capable of, what it's not capable of, and the software setup in order to get it ready for the experimental day. For the day of experiments, there's five phases, day of experiments. There's before every experiment. That is basically just all the setup that's needed to start the experiments and making sure that your crew knows what they're doing. And then before each experiment, you want to make sure everyone's wearing the proper PPE, behind cages, and their hands are over emergency stops in case there's some problems during the experiments. And then during experiments, you want to start recording. You want to monitor the robot in case that there is any unexpected problems that might occur. And if there is a failure of the robot, if the robot hits the platform or behaves erratically, make sure afterwards that you're checking the health of the robot. After the first trial is when you want to double check all your recordings, making sure they have the proper naming conventions and that motion capture doesn't have any blind spots of the markers. Afterwards is just resetting everything and making sure that the recorders are prepared for the next experiments. And then afterwards is basically just putting everything away and charging the robots and extracting all the data. And then after experiments is doing all your video and data processing and analyses. Part of my data processing was calculating the center of rotation. This was needed in order to perform proper transformations to get the marker locations in the treadmill frame from the world frame. In order to do this, I just performed an ICR using kinematics. This is where you take 2 time steps, the current and a future time step, and you get 2 locations of those time steps. For this, I use the front marker locations and the aft marker locations. And what you do is you connect a line between those 2 locations and then get the bisectors of those lines. And the intersection of those lines gets you the center of rotation. This is the equation I use to transform the markers from the world frame to the platform frame, first going to the treadmill frame. I also needed to calculate the approximate center of mass location of the robot from the experiments. This was done by getting the approximate location of each leg, the arm, and the trunk of the robot, and doing a weighted average. And then for my joint efforts, I also performed a gated average, which is basically a moving average of the data based on a full gate, which I estimated to be average of 37 time steps. A full gate is when a legged robot lifts up its foot and puts it back down. All right, getting to my results. So the standing experiments from Stiletto, this is what the data looks like for the joint efforts. I forgot to mention that I'm going to be looking at 4 different series. There's standing, walking in place, and the strafing and port to starboard plots, which you'll see after this. But standing experiments had the least amount of torques that could be seen in the data, and the walking experiments had the most similar amount of values. We can also see that as the wave states got worse, that the values increased and the value ranges increased. These are what all the plots look like. Typical trends is that the hips and adductors share similar values, but the knees have much larger values. This makes sense because the knees are what's holding up the majority of the weight of the robot. And another thing that I noticed is that the aft motors have higher torque values than the front. This is a little strange because the weight of the robot is towards the front, so you would think they would have higher torque values. Overall, like I mentioned before, the S curves and C states have much higher values, but the C state has higher averages. We can see that here. And the moving platform mode, which is a software that NRL wanted to use to help the stability of Spot. That was the moving platform mode, and those had higher average torques when it was being used than without. This is the gated average that I performed on the efforts. We can see that the aft motors, again, they still experience larger torques with the gated average performed on it, and that when the arm was deployed, there were higher torques than when it wasn't. We can also see that some of the outliers show that some of the gates had much larger values, and that the gates were consistently large torques. Compared to the non-gated average data, we can see that the plots are a bit more scattered, and that the minimum torque values do come to the surface, that we can see an average of the minimum gates torques. For Spot's controlled experiments, the both and just body experiments had much larger torques, and that when the arm was deployed, that it increased the torque values. And motion 2 out of the 3 motions had the largest values. Performing the gated average process on the torques for Spot and the control experiments didn't really show too much extra, but we can see that they did not create non-zero minimums, unlike what we saw for the Stiletto experiments, and that the majority of the data was there. The 25th percentile line was at 0. This shows that for a majority of the time, there was no torque, or for a large period of time, there was no torque for Spot. Vision 60's controlled experiment efforts. One thing that I noticed is that none of the motors reached their peak limits, but the continuous limits were being exceeded when we were looking at the averages. However, even with this knowledge, none of the experiments failed for Vision 60. We can also see that motion 3 of the experiments had the smallest amount of torques, and that motion 2 has the largest. Performing the gated average on the data shows that motion 2 has very large minimum values. And that the just body motion 3 has a very large average range box, which we can see here. We can also notice that the whiskers of the values are much longer, which shows that the majority of the data is at the higher torque limits or higher torque values. Comparing between spots, fields, and control experiments, we see that the maxes and the averages were similar between the field and control experiments. But the control experiments had larger knee values, whereas the field experiments had larger knee averages. The reason for this could be due to the type of motions that the robots experienced. Because the control experiments had a consistent left to right motion, that could explain the abductor values, whereas the field experiments had a consistent vertical motion, which would explain the knee values. Compared between Spot and Vision 60, we can see that the both and just body experiments, the experiments where the legs were in motion, had much larger maximums than the baseline. This is for both Spot and Vision 60. And it's most likely due to how the center of mass is shifting. We also can see that compared to Spot, Vision 60 has smaller arm torques than the baseline, and it could be due to the way Spot stepped during experiments. Vision 60 had 2 legs that stepped up and down, whereas Spot had 1 leg that stepped up and down, one at a time. Compared between the two, we also know that Spot has had larger torque maximums and that Vision 60 had higher averages. As I mentioned before, Vision 60 had those longer, lower whisker values, whereas Spot had longer upper values. So majority of Spot's torques were towards its bottom of what it had. Next, I compared the angles of the experiments, the joint angles of the experiments. Some trends that we saw during the stiletto field experiments is that, again, the C state and S curves angles increased as the wave states worsened, so that the C state and S curves were the worst out of the 4. And one thing that I noticed is that when the arm was deployed, there wasn't too much of a difference in what angles were experienced. And now is a good time to mention that during this field experiment, Spot was very unsteady during wave swells. As the boat hit a wave and the G-forces changed, Spot had a very difficult time moving about and staying in place. And for the stiletto experiments, there's also these other plots for the other experiment types. These long whiskers from the standing experiments and these range of outliers is most likely due to recording errors that was conducted. Either the recordings either started too soon or too late to ended too late. And that's why there are these values. Going over the video recordings, Spot didn't step at all during the experiments, and so they shouldn't have these large whiskers. Controlled experiments for Spot, you can see that all the values very similar, but when we look at the both experiments, we can see that the 50 to 70 or 25 to 75 percentile boxes are very small. And we can see the red mean line is at the top of the box, whereas the rest of them are at the bottom. This most likely shows that compared to the field experiments, compared to the field experiments, that the angles were much larger and more consistent. Vision 60 also had a very consistent range of angles that it had during the control experiments. We can see that during motion 3, the 25th to 75th percentile boxes were smaller and higher up. which shows that that there was a difference in how it stepped during motion 3. Either the robot didn't step as much, or the way it stepped was different during motion 3. The support polygon center of mass distance is the distance from the projected center of mass in the direction of gravity against the ground, whereas the support polygon is the connection between the feet of the robot. In this case, as the values get smaller, it's worse, because as the center of mass gets closer to the edge of the support polygon, the distance is smaller, meaning that the center of mass, when it exceeds the support polygon, the robot could potentially fall over. So when looking at these, we're trying to see what those smaller values are. And we can see that the smallest values come from motion, or from the both experiments across all 3 motions. And that if the maximum distance the center of mass could be for the experiments is at 78 millimeters, that more than half of them were exceeded 50% of that, the distance. And we can also note that this was during motions 1 and 2. The arm experiments had very wide ranges of averages. And yeah, motions 1 and 2 have the worst values. For Vision 60, we can see that those distances are much larger, which is a better thing. And that the worst center of mass distance was from the both experiments during motion 2. We can also see that the average is the smallest during the baseline experiments. Comparing between SPOT and Vision 60, as I said before, the center of mass distance, the support polygon, SPOT got to about 28% of the distance, whereas Vision 60 got to about 27%. They're fairly similar, but half of SPOT's was 40 to 59%, whereas Vision 60's worst was around 76% to the edge. Compared between the two, both experiments performed best during motion 3. It's motion 3. And for SPOT, the arm experiments were worse than the body experiments, but it's vice versa for Vision 60. Center of mass range. This is the X and Z range of its center of mass location projected on the ground. X is the forward and backwards direction, where Z is the left and right direction. For SPOT and the controlled experiments, we can see that the X direction, motion 1, has the largest values, followed by motion 2 per experiment, and that the both experiments have the highest values of the location range. Whereas in the Z direction, it's both experiments and the arm experiments are fairly large, which shows that when the arm is deployed, SPOT has more difficulty keeping its center of mass within the Z, on the Z axis. I should also mention that this plot is the robot frame, within the robot frame of SPOT, whereas this plot is the world frame, as what's seen in the world frame. Again, motion 2 has the largest X and Z ranges, and that both experiments have the largest range difference in the X direction, whereas in the Z direction, it's again the arm experiments that have the worst. This is an example of what SPOT's motion looked like, where we're looking down above the support polygon. This experiment here had the largest X range within the world frame, and this one was the largest Z range within the world frame. And we can see the center of mass moving about during the experiment. The right sides are within the robot frame, and the left sides are the world frame. And that's why we can see that spot adjusted a lot during those experiments. For Vision 60, in the X direction, the values don't change all that much. But we can see that Motion 2 does have the highest values. And in the Z direction, the experiments that use the arm, the both and the just arm experiments, have double the values as the baseline, or as the just body experiment. We can, if we look at the baseline here, we can actually see that the values are significantly higher than all the other experiments. And I'll get to that in a second. But we can see that the baselines are much higher than the others. In the world frame, we again see that the baseline is higher, and that much of the information is the same. And part of the reason is, unlike Spot, Vision 60 maintained its heading for the most part, whereas Spot moved around a lot. And these are the two experiments that had those large values during the baseline experiments, and we can see that these red lines show that there are spikes in the center of mass. And if we look at this experiment here, we can see that these transparent gray lines show that there was some crossing of the legs during one of the experiments. Comparing Spot to Vision 60, both Spot and Vision 60 had large Motion 2 values, which reaffirms that larger disturbances lead to larger center of mass ranges. And both Spot and Vision 60 had larger Z values when the arm was deployed, which shows that the arm does have a significant impact in the center of mass from the pitching motion. And we can also see that Spot's world frame and robot frame values were higher than Vision 60's. Now I'm going to talk about the standard deviation of those ranges, which shows the grouping of the center of mass. In the X direction for Spot, Motion 1 has the largest values in many of the cases, and the arm values are during the arm experiments, the range of averages are much higher or wider. And in the Z direction, we can see that the arm experiments have much higher values as well. In the world frame, we can see that in the X direction, the arm values are smaller, but in the Z direction, they're much larger. And we can also see that, again, Motion 1 has some of the highest values. For Vision 60 in the world frame, in both the X and the Z directions, the baselines were much smaller. Again, if we look at the baseline values from the center of mass range, it's because of those strange data spikes that we saw. But we can actually see that the baseline values are much smaller. And we can also see that compared to the both and the arm experiments, the just body experiments are much smaller. We can also see that the Motion 3 experiments, such as during the arm experiment, tends to have smaller values, and that Motion 2 impacts it worse. In the world frame, much of the information is again the same, much of the same. Comparing between Spot and Vision 60, Vision 60 has much smaller standard deviation values. For most experiments, Spot had about double the standard deviation distance, whereas some of them were 4 to 5 times of what we see in Spot when we're comparing between the same experimental experiments and motion types. But for both Spot and Vision 60, the body experiments were smallest in Z, but not the X direction. And for Vision 60, Motion 2 had the largest values, whereas for Spot, they varied between motions 1 and 2. Next, I'm going to get to the trajectory data. For Stiletto's field experiments, there were 2 cameras that were being looked at for the experiments. There was the front left camera and the left ceiling camera. These 2 cameras had the best view of Spot on the testing area, and so that's why they were selected. But they did have not a great view on the fiducials, but they were still better than the other ones. However, you will see that there is a difference between what the cameras picked up. There was also no ground truth for the experiments because they were conducted via joystick controller. And so it's not really possible to calculate the actual deviation error without a ground truth. These cyan lines, boxes, is the range of the standard deviation, whereas these arrows are the max and min of the position of Spot during the Stiletto experiments. We can see from this value or from this data that the wave states, as the wave states worsened, the value worsens just like the other data that I mentioned earlier. And that for some of the experiments that have the C state wave type, that they're actually a little bit smaller, and a possible reason is due to Spot's difficulty walking on the ship. And we can also see that the strafing experiments have larger values than we would think. And some background on that, the strafing experiments moved left and right, and so they should have larger Y values and smaller X values compared to the other experiments. Here's some examples of Spot on the treadmill. The left plot, or the left graph, has the X and the Y location with respect to time. This was during the at-pier experiments. And in the middle here, we can see Spot's X and Y position as it traveled during the experiment. The right side is during the S-curves motion type or wave type. And we can see that they're much more erratic and that the X values are much larger. We can also see in the at-pier experiment that the ground truth, why we couldn't use the ground truth, because the Spot did not walk in the same line every time. This is the left camera, left ceiling camera. We can see that in the standing experiments here that the values are somewhat all over the place, which is why it's not as reliable as the front left camera. But we can still see that as the wave states worsened, the position worsened. And this is ×5 speed of Spot at pier of the 2 cameras. On the left side is the front left. On the right side is the left ceiling camera. We can see that it's walking fine. And these other videos are of the S-curve experiments. We can see that Spot has a lot of difficulty moving in a line, and at some points right there can't actually move. We can also see that Spot's trunk bobs up and down during the S-curves. For the controlled experiments, Spot has similar values throughout, position values throughout. In both the X and Y direction, the arm and body experiments, 1 and 3 were similar. We can also note that the Y value averages are towards the front of the robot, which shows that Spot tends to move forward during the experiments, and the X value averages are towards the right, which also shows that Spot moves towards the right during the experiments. For Vision 60, the arm values are much smaller here, as you can see. And we can see that the both and the just body experiments have a large position deviation, which does show that the stepping in place increases the trajectory deviation. Comparing between Spot and Vision 60, they both had similar baseline values, X baseline values, and Vision 60 had larger Y baseline values. This could be because Spot did have some code function that kept it in place. Yeah. This is the trunk orientations during the control experiments. For Vision 60, the angles were the largest for the roll, pitch, and yaw during the both experiments. And that during those experiments, motion 3 had the largest roll and pitch, whereas during the arm experiments, motion 2 had the largest roll and pitch. And for the just body experiments, the roll, pitch, and yaw were the largest during motion 2. Vision 60's trunk orientation. Again, motion 2 has some of the largest values, which can especially be seen during the roll experiments and during the. We can also especially see with the roll angle during the both experiments. And I also observed that Vision 60's trunk tends to stay towards, tries to be arranged with the normal to the direction of gravity. And that whenever Vision 60 pitched upwards and backwards, that it changed its frequencies of stepping. Comparing between the two, Vision 60 has a larger range of roll angle averages, but a smaller pitch and yaw. And that for both Spot and Vision 60, motion 2 had the worst angles. And the last topic that I'll be talking about is the joystick input that was used during Stiletto's experiments and Vision 60's controlled experiments. Spot did not have any joystick input. What the data that is of interest is the linear X, linear Y, and angular Z value. And for Stiletto's experiments, we can see that there is non-zero linear Z, angular X, and angular Y data that was recording. And this is possible because it's a combination of Spot's internal data and what was used with the joystick inputs. We can see that as the wave states worsened again, the values tend to got worse, and that when the arm was deployed, the values actually got lower. Vision 60's controlled experiments. We can see that there is a lot of outlier markers, and just thin lines. This makes sense for the arm experiments as it didn't move at all, and these outlier markers is because that there's no 25th to 75th percentile box, which means any data that's not at 0, which is less than half of it, is non-zero. And we can see that both experiments are the only experiments that have a 25th and 75th percentile box, which means it did require more movement. And this is what I just talked about. Comparing overall between Spot and Vision 60, or between Spot's control experiment and field experiments, we can see that during the field experiments, everything got worse as the wave states worsened, and that Spot had difficulty walking during wave swells. Control experiments, Spot mostly had difficulty during motion 2. During those experiments of motion 2, which was the heavier treadmill motion, Spot had a lot of failures during testing, and that could be why the data reflects it. Between Spot and Vision 60, Spot seemed to overcompensate a lot for any disturbance from the treadmill, and I think that because Vision 60 didn't have any code that was trying to correct it, and that was why it was more stable. We also know that Spot's center of mass distance of support polygon was a lot smaller, meaning it was worse percentage wise, and that Vision 60s were a lot better, and that the center of mass location range and standard deviation values were much higher than Vision 60s. And Spot also generally had larger displacements, trajectory deviations than Vision 60. And lastly, Vision 60 tended to appeared to be more stable when the arm was in use. This is what I contributed for my thesis. Testing and safety procedures for legged robots, dynamic surfaces, the construction of safety harnesses and other apparatus, the identification of the IMU, shipboard motions, and an evaluation of the two robots. This is my one publication that I have, and I would like to thank NERV and its staff for letting me use its facility and all their equipment, and NRL for sponsoring the project and helping set up the stiletto trip. I also want to thank my advisors for guiding me and for my lab partners who helped me conduct my experiments. Thanks for being here. Mute, okay.
All right, we go for a question from audience.
I have a couple questions here.
Okay.
So you mentioned that in the stiletto experiments, they have this moving platform mode. Can you go into a little bit more what that is?
For the moving platform motion?
Yeah.
Okay, so I had originally thought that this was something that Boston Dynamics had for part of their was a mode that Boston Dynamics created. Oh, sorry. I thought the moving platform motion, which Brendan is asking about, was created by Boston Dynamics as a feature that they were using, but upon looking into it, it wasn't. I reached out to staff at NERV and Boston Dynamics, and they didn't know what it was. So it's most likely something that NRL installed onto their Spot, because that was their Spot that was used in the stiletto experiments. And it was meant to make Spot more stable when it was on a moving platform.
But you found that it did the opposite, it seems.
It somewhat did.
Okay.
But it also used up a lot more torque in order to do so. Yeah. I hope that answered that.
Yeah. So my next question is, in the control experiments, you didn't show any joystick inputs for Spot. Why is that?
So Spot's control experiments used some of Spot's SDK examples by Boston Dynamics, and part of those examples was Spot was tracking with its arm the fiducial on the platform, and part of that example is having the body follow Spot, and so there was no joystick input that was needed.
One last question. So kind of your overall big thing is this comparison between these two systems, the V60 and the Spot.
Yeah.
If I owned a boat and I wanted a robot dog on my boat, what would you recommend I get?
Okay, that's a harder question. So in the end, Vision 60 doesn't have any software right now, as of right now, to use any fiducials or any other setup to automate its procedures, but Spot does as of right now. Spot already does have things where it can manipulate like screwdriver, for example, open doors, stuff like that. So right now, Spot, although the data did show that Spot was worse than Vision 60 in the control experiments.
Thank you.
Yeah.
Other question. All right.
I don't know if there's any other questions on.
No, there is none on the Zoom. So we thank you again, and people can leave, come back for cookies and coffee, or take it ready.
Yeah, take some cookies. They're homemade.
All right. You stop recording.
Okay.
Don't turn off the Zoom. But
Okay.
stop it.
Everyone out. Oh, actually, what about Jan and Professor
No,
Druck?
just stop recording.
Oh, stop recording.
Yeah.
Okay.
Keep the Zoom on. Let's see.